Hello everyone. Yeah, welcome to the session. Please wake up after lunch. So, I'm Dmitry Khhovratovich, and this is joint work with my colleague Mikhail Vladimirov. So we represent the University of Luxembourg and a small company called EDCON. And this talk is devoted to secure token development and deployment. So you may notice some ambiguity in the title. That's indeed both about... Okay, so... The other one. Oh, that's much better. Okay. So, you see some ambiguity in the title. That's somewhat intentional. So we don't just develop and deploy secure tokens, but we also talk about secure development and secure deployment. So why the token stuff is important, you have just previously heard from the first speaker of the session. He reminded us that quite many ICOs happened last year, and predicted that over 300 will happen this year. So if you one of them who plan to raise some small amount of millions of dollars this year, then it's for you, this talk. Listen carefully. So the ERC20 standard that deals with tokens is actually quite small, quite compact, and there are only 6 functions there. So you might question, well, what can be a problem with a contract with just 6 functions that may not just even does accept Ether? So what the problem can be? So only 6 functions, like to learn how many tokens are in circulation, the constant function. You can learn the number of tokens belonging to a certain address. You can transfer tokens from your address to another one. And there are 3 other functions with quite interesting functionality. This approve and transfer from a group of functions. So the idea is that a user can, a token owner doesn't have to transfer directly his tokens to someone, but it can approve another person, another account or contract with withdrawing the tokens from his account later. The idea is to, so that some contracts like exchange contracts can withdraw these tokens and get notified about it immediately. So the user is supposed first to approve another account with a certain number of tokens, and then the other account can withdraw these tokens in multiple sessions or in a single one. And there is an allowance function, the constant function, that can tell you how much B can withdraw from you. Well, this looks pretty simple, right? So, nevertheless, the security of these contracts is a vital issue, because it's a standard, de facto standard, and we're not talking about a single contract deployed, but we're talking about many contracts. So if we see like 300 contracts in the future dealing with tokens, and everyone repeats the same error or the same like anti-pattern of software development, that's not quite good, and there is a possibility of token loss, or in the better case, availability loss. For example, when external contracts may have problems with interacting with your token smart contract. So this will not lead to token loss, but they may lose gas, or your token might not be adapted properly by exchanges. You will not be able to distribute rewards to people. That can be quite bad. And these threats are typically caused by vulnerabilities. So the insecure code, most of you know it. And another common vulnerability is that the interface is too complex, and as a result, regular users cannot interact with the contract properly. They make mistakes. They insert extra zeros or delete zeros. They miscalculate the number of tokens to withdraw, to send. That's all the kind of problems that result from non-ideal interaction with the contract. So the question is also how to deploy, how to operate the token smart contract properly. So not just how to deal with insecure code. So the current insecurity of smart contracts, so some of the slides will be devoted to insecurity of existing implementations. So let's look at some like random, before we look at the code, I quickly remind you of exceptions in Solidity. So exceptions is such a tricky thing that it cannot be caught. Well, you can catch an exception, but you cannot get the value at the same time. So for example, suppose there is a contract C1 that under some condition throws an exception, and there is a contract C2 that calls this C1 with first calling the function f directly, and second one using the call function to call f and passing the hash of f as a parameter, well, as usual. So the thing is that the first call cannot catch exceptions, and the second call cannot get the value returned. So it's a problem because if you don't catch exception, it will boil up to as the earliest call, to the nearest call in the stack. And if there is no such call, it will just propagate and the transaction will fail, entire gas will be lost. That's also not quite good. So we declare that exceptions should be reserved for exceptional events. So until some very unfortunate circumstances, your contract shouldn't throw exception. It just should return true or false, whatever declared by the standard. And as a result, the external contracts will have more confidence in calling your contract with some non-trivial functions like transfer from. So why is this important? Let's consider some random code from internet. Here's the example, a snippet of a token contract with the transfer from function. So I remind you that the idea of transfer from is that one is, you don't see mouse here, by the way, okay, doesn't matter. So the idea of transfer from is to withdraw some number of tokens from and send them to. And you see there is a balance array which is modified. There is allowance array that is figured out how much one can withdraw. And after successful transfer, the allowed array is also modified. And you see there is no here, there is no direct addition or subtraction, but there are functions called SafeAdd and SafeSub. So these are functions from SafeMath sublibrary, also quite popular. And here is an example of SafeSub here. And you may ask why exceptions, because you see in SafeSub, in the first line of SafeSub, there is a third. And if B, so it's supposed to subtract B from A, but if B is bigger than A, then assert will throw exception. And you see that this exception can be thrown in third or fourth line of transfer from. So whenever SafeSub is called, an exception may be thrown there. Okay, so let's look a bit closer. So if the balance is insufficient or the allowance is too low, so we cannot physically transfer a necessary amount of tokens from one account to another, then exception will be thrown. It's not evident from the code because the exception is like deeper in the SafeSub function, but it's true. And what's more important, that the standard requires us to return false in this situation. But you don't see that the false is not returned here. Well, you see that there's no return false, but it's a bit unclear what SafeSub does. Maybe it throws exceptions, maybe not. Maybe there are always like return true. So you have to look deeper in the SafeSub and figure out how it works. It's not ideal and not clear. Even a bit worse development pattern you may see here. That is a marvelous example of inverse control flow. So you see that in the first in the line balance 2, where the balance 2 is increased before all the checks, all the conditions are checked, all the conditions are satisfied or not satisfied, we first increase the balance of the receiver. And if something goes wrong, if the balance of the sender is insufficient, we have to revert the operation. But we don't like decrease back the balance of the receiver. Instead, the code developer just decided, let's throw an exception in SafeSub. And the idea is that like if the balance of if the allowance is insufficient, then this line, the allowed line, will throw an exception that will affect the balance line here. So the condition is actually checked 2 lines after, then it should be applied. So it's a bit like a weird control pattern, and well, it's nice that here only 2 lines of code between those two. But if there are more, that's very untrivial to catch. Also, a bit of approach that we don't quite recommend is when we deal with SafeMath. There is an approach that, well, the idea of safe functions is to prevent overflows. But the strategy that is currently employed is to first like make an operation and try to detect if overflows happened or not. That's not quite good because the correctness of this function, it relies on our understanding how overflows works in Solidity, which is not like properly documented, and worse enough, it can change in the future. So the contract that handles overflow properly, it may not handle it properly after the Solidity compiler changes. And well, it's actually in this case, it's not quite trivial to prove that there is no, the overflow here is thrown exactly when, the exception is thrown exactly when the overflow happens. And the same with safe addition and safe subtraction. Okay, so that was like contract insecurity. So there is also another insecurity in the approve function. And there's actually an attack on the standard, we call it, because it's possible that user misinterpret the ERC20 standard, and the following situation may occur. So suppose that Alice first approves Bob with sending n tokens. And then at some point that Alice says, okay, well, I gave him too much. Maybe he should get not n, but n over 2, well, another number m. And Alice decides, okay, all right, I'll send another transaction, because by standard it overrides the original Bob's allowance. Okay, so Alice approves him with m tokens. And Bob just noticed this transaction happens and realizes, okay, Alice is going to change my allowance. Well, let me first withdraw my tokens. And then Bob tries to inject his transaction right before the Alice transaction is mined. And he withdraws n tokens from Alice before Alice transaction is applied and Bob's allowance changes. After Alice transaction is mined, Bob easily withdraws m more tokens from Alice and takes m plus n in total. It can be much worse when Bob sends all these tokens not to himself, not to him, but to some another user, Carol, because the transfer event that is logged during the transfer from function, it doesn't log who called transfer from, but it also only logs the sender and the receiver. So Bob will be excluded, Bob's address will be excluded from all the events. It's actually not so trivial to figure out who called the function. So our suggestion here is to, which we actually now actively discussing with the community, is to make a new function which we call atomic approval. So it first checks that the current allowance value is equal to the current value, and if it does, then the new approved value is set. And we also include the spenders into two events. So the signature changes, and we include one more parameter. So the spender in transfer and the old value of the approval into the approval event. So these functions will completely solve this problem. That's not the end. So our approach goes a bit beyond finding bugs and picking holes in existing code. So we program our own contracts, and here we follow the strategy that first define functional requirements clearly for the token contract, and the APIs describe all possible use cases. Well, you may think there are not so many use cases, but for transfer from, quite many of them. So there's like main flow in transfer from that goes fine, but there are like 4 more exceptional flows that are untrivial to detect, and uncareful and careless programmer may miss while doing it. And of course, all the use cases are covered by tests like this. So this is just an example of a small test covering one use case before. So that's what we actively suggest. So our transfer from function is fully compliant to the ERC20. There are also other functions implemented. So the entire ERC20 standard is implemented with this secure by design strategy. And the last but not least is that to deploy and to administer the token contracts, you need not just a secure code, but a proper user interface. And the idea is of user interface that to simplify the job for a person who would administer the token contract for some operator. And of course, because smooth user experience is crucial for security. If the experience is not easy, then the user will invent some life hacks like write passwords on a door or send them by email. So all this sort of stuff we would like to avoid. So easy user interface, clear, transparent, not extra details, runs in browser. Well, MIS browser is not necessary, but supported. It connects to local or remote node, may work offline, online, and has some plugin support for administrator consoles. So an example of like this. So we have already wallet implemented, and this wallet works with tokens. So you can actually add any token, mainnet, testnet, whatever, and work with them connecting to a remote node, currently running on Amazon EC2. And it's actually a static file, just pure JavaScript. And for users, they have easy view on their balance, exchange rates, and transaction history, and the proof and allowance functionality, of course. And for token administrators, some more stuff like foolproof token supply, freezing transfers, like multisig support in the administrator contract. It everything looks like this. And well, the message is whenever you need a secure code and smart and helpful UI, feel free to contact us.